Reinforcement learning is a learning paradigm where systems improve behavior through interaction with an environment. Instead of learning from labeled examples, models learn by receiving feedback in the form of rewards or penalties, allowing behavior to evolve over time. Learning occurs through experience rather than instruction. Actions are taken, outcomes are observed, and feedback guides future decisions. Reinforcement learning systems consist of agents, environments, actions, and rewards. These components define the interaction structure. The agent is the decision-making entity. It observes situations and selects actions to influence outcomes. The environment represents everything external to the agent. It responds to actions and provides feedback. Actions are the choices available to the agent at each step. They determine how the agent interacts with the environment. States describe the current situation. They summarize information needed for decision-making. Rewards provide feedback on actions. They signal whether outcomes align with objectives. The reward function encodes the goal. It defines what the agent is trying to optimize. A policy defines how actions are selected based on states. It represents learned behavior. Value functions estimate expected long-term rewards. They guide decisions beyond immediate feedback. An episode spans from an initial state to termination. Learning often occurs across episodes. Exploration involves trying new actions. Exploitation uses known effective actions. Balancing exploration and exploitation is critical. Too much of either degrades performance. The learning objective is to maximize cumulative reward over time, not immediate gain. Delayed rewards complicate learning. Actions may influence outcomes far in the future. The Markov decision process formalizes reinforcement learning mathematically. Model-free methods learn directly from experience without modeling the environment. Model-based methods learn environment dynamics and use planning to choose actions. Q-learning estimates action values to guide optimal choices. Policy gradient methods directly optimize policies, especially for continuous actions. The learning loop involves observing, acting, receiving feedback, and updating behavior. Training often occurs in simulations. Deployment applies learned policies to real systems. Reinforcement learning can be data inefficient. Many interactions may be required. Exploration can be risky in real environments, requiring constraints and safeguards. Simulations provide safe, repeatable learning environments. Games have been important test beds due to clear rules and rewards. In robotics, reinforcement learning supports control and motion planning. Some recommendation systems use reinforcement learning for sequential decision-making. Industrial applications include scheduling and resource optimization. Learning is difficult due to sparse rewards and long decision horizons. Training instability and sensitivity to parameters are common challenges. Poorly designed rewards can lead to unintended behavior. Safety concerns arise when agents exploit loopholes in reward design. Training can be computationally expensive and time-consuming. Real-world data collection limits scalability. Unlike supervised learning, reinforcement learning uses feedback rather than labels. Unlike unsupervised learning, it is explicitly goal-driven. Human guidance can shape rewards and improve learning outcomes. Today, reinforcement learning is used selectively rather than universally. It works best in controlled environments with clear objectives. It struggles in uncertain or poorly specified settings. Ethical concerns include behavior manipulation and accountability. Governance requires monitoring and constraint mechanisms. Strengths include adaptability and long-term optimization. Limitations include complexity and resource demands. A common misconception is that reinforcement learning implies general intelligence. The core idea is learning from consequences rather than instruction. Reinforcement learning is a specialized tool within the AI ecosystem. Next, we will recap learning paradigms and compare how machines learn across approaches.